All right, let's dive right in. We're going to take something that looks impossibly complicated and show you how, at its heart, it's actually beautiful and surprisingly simple.
Okay, so you open up a textbook, right? And bam, you get hit with this. It just looks like a total wall of symbols, like a secret code meant to scare you off. But what if it's not? What if the big idea behind all of this is actually really simple, something we can totally get our heads around in just a couple of minutes? Well, that's exactly what we're going to do. We're going to tear down that wall and find the beautiful, simple idea hidden inside.
All right, so first things first, let's stare this thing down. Where on earth does a formula like this even come from?
This thing comes from a field called coding theory. And look, I know that sounds super academic, but it's not just abstract math. It is the invisible engine that runs our entire digital world. It's the reason the messages you send actually get there, why your music streams without glitches, why your data doesn't just get corrupted. It is so important. But as you can see, the language can be a little dense.
So how do we get past it? How do we break through that wall? Well, you look for the hidden structure. See, here's the secret. Most of these super complex-looking systems, they're built on just a few really simple rules. So let's go find them.
And in this case, that hidden structure is something called a mathematical group. Now, don't let that name freak you out. A group is really just a set of things, could be numbers, could be actions, whatever, and a single way to combine them that follows a couple of simple, almost common sense rules. And what's so wild is that this entire powerful idea is built on just 3 rules. That's it, 3. First, you've got associativity. All that means is it doesn't matter how you group things when you're combining them. The order of operations doesn't change the final answer. Second, there's always a neutral element. Think of it like the number 0 in addition. It's the one thing you can combine that does absolutely nothing. And third, every single thing in the group has an inverse element. A partner, basically, that undoes the operation and gets you right back to that neutral do-nothing element. See? Simple, right? Let's see what this actually looks like in practice.
Okay, we're going to start with a concept from logic, and I guarantee you use this every single day without even realizing it. It's called the exclusive OR XOR for short. You can think of it as the logic of strict choices. It's only true if one input is true and the other is false. It is literally the definition of one or the other, but not both.
Here's the perfect way to think about it. If you say to a friend, I want a salad or a sandwich, and they bring you both, you're probably not going to be mad. That's a regular, inclusive OR. But if the menu at a restaurant says your meal comes with a salad or a sandwich, you know what that means. It's an exclusive OR. You got to pick one. You can't have both. And that, right there, is the core idea.
And you see this logic all over the place. Think about your privacy settings on social media. Is your profile public or friends only? It can't be both. And this is the really important part, it is a cornerstone of cryptography. If you take your secret message and XOR it with a key, you get scrambled nonsense. But here's the magic. You take that scrambled nonsense and XOR it with the exact same key, and your original message pops right back out. It's a perfect, real-world example of that inverse element we were just talking about.
Okay, so that was logic. Now let's switch gears and look at a tiny, little self-contained universe of numbers. And trust me, this is where it gets really, really cool.
We're just going to use 3 numbers. That's it. 0, 1, and 2. And our special operation is called addition modulo 3. Now, I know it sounds a little fancy, but all it means is we're adding, but on a clock that only has 3 hours on it.
This little table here, this is the entire universe. It shows us everything that can possibly happen. So let's see. 1 plus 1, that's 2. Easy enough. But what's 1 plus 2? Well, 1 plus 2 is 3, but on our 3-hour clock, the number 3 is the same as starting over at 0. So 1 plus 2 is 0. How about 2 plus 2? That's 4. So on our clock, we go 1, 2, 0, and one more step lands us on 1. See how that works? Everything just wraps around, and we always stay inside our little world of 0, 1, and 2.
So the big question is, does this little system follow our 3 rules for being a group? Let's check them off. Rule 1, closure. Are all the answers in this table a 0, a 1, or a 2? Yep, every single one. We can't escape the set. Check. Rule 2, identity element. Is there a do-nothing number? Well, look at 0. Adding 0 changes nothing. Check. Rule 3, inverses. Does every number have a buddy that brings it back to 0? Well, for 1, its buddy is 2.
because 1 plus 2 is 0. For 2, its buddy is 1. And for 0, well, its buddy is just itself. Check. It follows all 3 rules perfectly. This, my friends, is a group.
Okay, so we have these super simple, really elegant rules. We've seen them in action with logic, and we've seen them with this tiny little circle of numbers. Now, it's time for the payoff. Let's go all the way back to the beginning.
Remember this stuff? All that academic language about a cyclic code that is invariant under the cyclic shift. It just sounds so abstract and complicated, right?
Well, get this. That cyclic shift, that's exactly what we were just doing. It's the wrapping around on our little 3-hour clock. Those incredibly powerful error-correcting codes that were described with all that dense language, they are built on the foundation of these simple, perfect, elegant little groups. The complexity isn't the point. It's just an application of the simplicity.
And why should you care about any of this? Because these simple rules, they're not just a math trick. They are absolutely everywhere. This is the bedrock of the error correction that let your scratched-up CDs still play music perfectly. It's fundamental to the cryptography that keeps the entire internet secure. And it goes even deeper. Physicists use this to describe the fundamental symmetries of our universe, all the way from tiny subatomic particles up to Einstein's special relativity. Chemists use it to understand the actual structure of molecules. It's kind of the secret code of reality itself.
So the next time you run into a wall of symbols, maybe don't be so intimidated. Remember that behind all that complexity, there might just be a few simple, beautiful rules waiting for you to find them. Which makes you wonder, right? What other huge, complex ideas out there are just one good explanation away from making perfect sense?